Okay, let's continue our discussion of the simple Haar wavelets, part B, ordered fast Haar wavelet transform. We will actually develop the code, the computer code that will code up this algorithm, but we'll start with the sample structure that code that we'll discuss in the second half of the screencast uses. So let's go with a simple sample of two entries. The sample size has to be an integral power of 2. So, and this sample size consists of the first half, S1 sub 1 over 2, and S2. So the first half of the sample and the second half of the sample. So no surprises here. Let's go and consider another sample of size 4, 7, 3, 4, let's say 10. Okay, so this sample consists of okay, there's an entire sample, then there are 2 halves of the sample, and then there are 4 quarters of the sample. So the first half, the sample consists of the first half, 7, 3, of the second half, 4, 4 and 2, and then of the 4 quarters, 7. So the first quarter, which is it's actually the first half consists of 2 quarters. So the first quarter and the second quarter, and then the second half consists of quarter number 3 and quarter number 4. So then 7, 3, the third quarter is 4, and then the fourth quarter is 10. Okay. Well, let's consider another one of 8 elements: 5, 3, 2, 6, 10, 8, 11, right? So 1, 2, 3, 4, 5, 6, 7, 8. So this sample consists of 2 halves. So second half, so then we have 4 quarters, and then 8 1/8. So the first 1/8, the second 1/8, okay, and then, well, I'll drop the subscript. It's kind of hard to write the subscript of 1/8. So the third 1/8, the fourth 1/8, the fifth 1/8, the sixth 1/8, and then the 7th and 8th. So 5, this is the second 1/8, 3, then we have 2, 6, 10, 8, and 8, and then 11, okay. Let's go through 3 examples that we will test our source code on. So let's say 7, 3, And so let's use this notation. That's a to the first. That's our a coefficients. That's the original average coefficients. That's the original sample. And that superscript of 1 actually tells us the number of sweeps that the ordered fast Haar Wavelet transform algorithm will use to process this sample. So it's the length of the sample is 2, and then the number of sweeps is the log to the base 2 of that number, of the length of the sweep, which has to be an integral power of 2. So the log of n in this case is 1. So we need only 1 sweep to process this sample. Okay, so how do we do this? Well, the first sweep, right, brings us to the level of 0, and we just have apply the basic Haar Wavelet transform to the each subsequent, each consecutive pair of indices. So the average on the 0th level is 7 plus 3 over 2, and the Haar Wavelet coefficient on that interval is 7 minus 3 over 2. So this gives us 5, and this is 2. Okay. Okay, so the approximation, the function, right, represented by this transform is 5 times phi of a closed interval from 0 to 1, closed on the left and open on the right. 0 included, 1 excluded, times 2 psi from 0 included to 1 excluded. This is 5 is the average, and 2 is the modular value of the wavelet that the value of the sample changes from the first half, in other words 7, to the second half 3. So because 7 plus minus 2 times 2, minus 2 is the size of the wavelet, is 7 minus 4 equals 3. So, which is indeed what we have. Okay, and then let's work out another example, 7, 3, 4, 10, right? This is the second sample. So the number of sweeps is 2, right? So n equals 4. So number of sweeps log to the base 2 of 4 equals 2. So the first sweep is 2 minus 1, so the first sweep. Eventually we'll go from a to the 2 to a to the 0, and then we stop. So so the first sweep is 7 plus 3 over 2, 4 plus 10 over 2. So and then the wavelets, wavelet coefficients, or the C coefficients. C at the first sweep is going to be 7 minus 3 over 2, 4 minus 10 over 2. Okay, so this is 5, 7, and this is 2, and minus 3. Okay, and after each sweep, we're going to put the A coefficients at the beginning of the array. And remember, their number reduces by factor of 2 at every sweep. So the new array is going to be 5, 7, and then 2 and minus 3. And then the next sweep, right, sweep 2, will only work on the first 2 A coefficients. We're going to forget about the C coefficients because they're already computed on that level. In order to compute the C coefficients on the next level, we only need the A coefficients from the previous level. So sweep 2. Okay, so this is the 0. 5 plus 7. And then this is the only A coefficient, and then the C coefficient, or the wavelet coefficient on that level is 5 minus 7 divided by the 2. So this coefficient is 6. And the C coefficient over the entire sample is 5 minus 3 over 2, 5 minus 7 over 2, right, minus 1. Okay. Okay, so what does it mean? Well, it means that the f tilde, the approximation of this sample, is 6 times 5 from 0 included to 1. So the 6 is the average plus minus psi 0, 1. Right? And then plus this is the coefficients on the next level. 2 times 0 psi time on the level from 0 included to 1 over 2 excluded, plus minus 3 psi from 1 over 2 included to 1 excluded. So again, we talked about it in the previous screencast, but it's a good thing to review. So what is 6? 6 is the average value of the sample. So if we add up 7, 3, 4, 10, and divided by 4, we're gonna get 6. So 7 plus 3 plus 4 plus 10 divided by 4 equals 6. So minus 1 is the that's the coefficient of the wavelet that shows how the average of the first half changes to the average of the second half. Right, so the average of the first half, 7.3, right, changes to become the average of the second half, right? So okay. All right, and then by so it changes by minus 2 times minus 1. In other words, 2, right? So 7 plus 3 over 2 plus 2. Right? The average of the first half plus 2 equals 7, which is 4 plus 10 equals 4 plus 10 over 2. So that's the average of the second half. So this for how 5 changes to 7. Okay, this is what these coefficients mean, and then so this is how the signal changes from the first quarter to the second quarter, from 7 to 3, right? Because 7 plus minus 2 times 2 is 3, and minus 3 is how the signal changes from the third quarter to the fourth quarter, from 4 to 10. That's what this coefficient minus 3 means. Okay, so let's do another sample, and then we'll take a look at the source code. So 1, 2, 3, 4, 5, 6, 7, 8. Yes, so 8. So it's integral power of 2. So n is equal to 8. So we're gonna have 3 sweeps. The number of sweeps is equal to log of to the base 2 of 8, which is equal to 3. So at the level 3, which is the original level, we just have coefficients. That's the input. 5, 3, 2, 6, 10, 8, 11, 11. Okay, so the first sweep is 3 minus 1. So 5 plus 3, that's the average. 2 plus 6 over 2. 10 plus 8. 11 plus 11 divided by 2. Okay, then C. Okay, 5 minus 3 over 2. 2 minus 6 over 2. 10 minus 8 over 2. 11 minus 11 over 2. Okay, so 4, 9, 1 minus 2, 1 and 0. So 4490. We're going to put the A coefficients, the head of the next sample, and then the C coefficients at the end of the sample. Okay, so sweep 2. Three minus 2, the second sweep. 4 plus 4, 9 plus, oops, I made a mistake here, so it should be, of course, 11. 11 plus 11 over 2. I apologize. So, and this is also should be 11. Okay, So 9 plus 11 divided over 2. C 3 minus 2 equals 4 minus 4 divided by 2, and then 9 minus 11 over 2. Zero, and then minus 1. Okay, 10. All right. So we're going to put these, right, the A coefficients, the head, then the next goes the new C coefficients, and then the other C coefficients come from the previous level. Oh, we just don't change them. They're already in the array. And then sweep 1, sweep 3. Okay, so 3 minus 3, that's the level 0. Only have two values, 4 plus 10 divided by 2, and then C 3 minus 3 equals 4 minus 10 over 2. So this will be 7. And the wavelet over coefficient over the entire interval is minus 3. So it'll be 7 minus 3 is 0. Or just minus 1, 1, minus 2, 1, and 0. Okay. So we can write it out. So this the approximation function f tilde is going to 7 times phi on the level from 0 to 1, 0 included, 1 excluded, then minus 3 times psi on the interval from 0 to 1, 0 included, 1 excluded. Plus 0 times psi from 0 to 1/2 plus minus 1 psi from 1/2 to 1, so the second half of the sample. Okay, I'm running out of space, so I'm likely make some mistakes, but the next coefficients should be 1, minus 2, 1, and 0. And those are the wavelet coefficients on the first quarter, on the second quarter, and on the third quarter and then the fourth quarter. On the first quarter, the coefficient is 1. On the second quarter, the coefficient is minus 2. Then on the third quarter, the coefficient is 1. And on the fourth quarter, there's no change, so the coefficient will be 0. So that's what this approximation function represents, and that's what the ordered Haar wavelet coefficient gives us. And why is it called ordered? Well, because the wavelet coefficients are ordered from the lowest frequency to the highest. So we're going to have the coefficients working on the whole interval, then on half intervals, then on halves, then on quarters, then on 1/8, then on 1/16, and so forth, depending on the length of the sample that we're processing. Okay, so then we can talk about let's talk about the source code. So, and instead of just writing the source code, we'll go over the Java code because it's fairly straightforward of what we to convert the ideas that we have developed in the previous two screencasts. So the previous screencast 4a. And then 4b, which is this screencast, and we're going to run it on these three samples that we manually worked through. Okay, so ordered. So we get a sample, which is the array of double. So we get its length. If the length is not evenly divisible by 2, we return because n must be an integral power of 2. If it is not, then the ordered fast Haar Wavelet transform algorithm cannot work. Then we're going to figure out the number of sweeps just by taking the log to the base of 2. In Java, log is computed to the base of 10, so we have to divide by the log to the log 10 of 2. If the number of sweeps is number 1, that means that the sample is of length 2, and all we have to do is compute the A coefficient as the average of the first two values, the only two values, and then the C coefficient as the wavelet. Set the sample. Sample gets destructively modified. The first element of the A coefficient, the second element of C coefficient. If we are greater than 2, then we just have to sweep and compute the C coefficients and the A coefficients from the consecutive pairs. Right. So the size is basically you can think of the size as the level, right? So at sweep 1 we have 4 coefficients, at sweep 2 we have 2 coefficients, so at 3 we have 1 coefficient, well, 1 A coefficient and 1 C coefficient, right? The number of A coefficients equal the number of C coefficients at every level. So we allocate the appropriate arrays to store A coefficients and C coefficients. These are just two indices that will allow us to iterate over these array AI and CI. A index and C index. Okay, so that's the end. End is the index of the last A coefficient in the sample at sweep number, sweep num. Right, so in the comments actually gives you the formula, and then we iterate over the sample and compute the A coefficients and C coefficients and store them at the appropriate spots in A coefs and C coefs arrays. Okay, so and then we have basically this for loop puts the A coefficients at the head of the sample, and then C coefficients right next to them, to the right of all of the appropriate C coefficients, right? And so the next sweep will only be using only the first quarter half of the sample, depending on the level, right, that we placed. And then at the end, when we only have two values, we compute the overall A coefficient and the overall C coefficient. So A coefficient is the average over the entire sample, and C coefficient is the wavelet coefficient. Okay, so that's roughly what we need to do. That's exactly what we need to do. I was not, and then I was not aiming for efficiency. It's just transparency was my aim. So, and this is just a test function that tests what we have implemented on the three samples that we have worked out manually in the previous screencast. No, actually, in the first half of this screencast, rather. Sorry. Okay, so we're just gonna run it and. The results will agree with what we have worked out manually in the first half of this screencast. So let me run this, and you can see. So the first sample when we apply the ordered fast Haar Wavelet transform, we get 5.2. the second sample, the result of applying ordered fast Haar wavelet transform gives us 6 minus 1 to minus 3, and then the fourth is the result of applying the ordered fast Haar wavelet transform to the third sample. Okay, well, this is to be continued. Thank you.